Hello, welcome to the 10th video session of digital image processing. In the last session, we have discussed image sharpening using frequency domain filters, ideal high pass filter, Butterworth high pass filter, Gaussian high pass filter, the Laplacian in frequency domain, unsharpening, high boost filtering, and high frequency emphasis filters, homomorphic filters. Today, we are going to discuss image smoothing using frequency domain filters and selective filtering. So our contents today are image smoothing using frequency domain filters, ideal low pass filter, Butterworth low pass filters, Gaussian low pass filters, selective filtering, band reject and band pass filters, notch filters, and finally we will go for MCQ. Image smoothing using frequency domain filters. Smoothing is achieved in the frequency domain filters by attenuating high frequency components by applying low pass filters. The change in the frequency, that is the rate of change of intensity per pixel, let's say some region in the image that changes from white to black. If it takes many pixels to undergo that change, its low frequency, the fewer the pixel takes to represent that intensity variation, it's higher. Purpose is to reduce the blur or noise reduction. Blurring is usually used in pre-processing steps, equivalent to low-pass filtering in frequency domain because smaller details are removed. Smoothing is achieved in the frequency domain by high frequency attenuation, that is by low-pass filtering. So we get edge blurring. These are the side effects of this smoothing. There are three types of low-pass filters. We employ three types of low-pass filters: ideal low-pass filters, Butterworth low-pass filters, Gaussian low-pass filters. Ideal low-pass filter is specified by the function h of u comma v is equal to 1 if d of u comma v is less than or equal to d naught, and it is 0 if d of u comma v is greater than d naught, where d naught is a positive constant and d of u is the distance from u of v to the center of the mask. The sharp cutoff frequencies of an ideal low-pass filter cannot be realized with real electronic components. That means it allows all the frequencies within the cutoff frequency of within the circle of cutoff frequency of d naught from the origin. It does not all the frequencies which are outside the circle. It is called as low-pass filter. So here you can see the perspective plot of an ideal low-pass filter transfer function. In the figure A, figure B is filter displayed as an image. Figure 3 is the filter radial cross section. Here you can see from the figure test pattern of size 68 into 68, 688 into 688 pixels. B is its Fourier spectrum. The spectrum is double the image size due to padding, but it is shown in half size so that it fits in the page. The superimposed circles have radii equal to 10, 30, 60, 160 and 460 with respect to the full size spectrum image. These radii enclosed 87, 93.1, 1.1, 90, 95.7, 97.8, and 99.2% of the padded image power respectively. The right side figure, the figure here is the original image. Results of filtering using ideal low pass filters with cutoff frequency set at radii values of 10, 30, 60, 160. The power removed by these filters was 13.6.6, 6.9, 4.3, and 0.8% of the total respectively. Butterworth filters, Butterworth low pass filters. The transfer function of a Butterworth low pass filter is defined as h of u comma v is equal to 1 over 1 plus d of u comma v by d naught to the power of 2 to the power 2n, where d naught is the cutoff frequency. In the figure is a perspective plot of a Butterworth low pass filter transfer function. Figure B is a filter displaced as an image. Figure C is a filter radial cross section of order 1 through 4. That is plot of transfer function of with respect to d of uv. So here in the figure, you can see the spatial representation of Butterworth low pass of order 1, 2, 5, and 20, and corresponding intensity profiles to the center of the filters. Observe how ringing increases as a function of filter order increases. You can see the ringing is increased as the order is increasing. Order of the filter is increasing. Gaussian low pass filters. The Gaussian low pass filters in 2 dimensions are given as h of u comma v is equal to e to the power of minus d square u of v by 2 sigma square, where d naught is equal to spectrum. In the figure, you can see the perspective plot of Gaussian low pass filter transfer function. B is the filter displaced as an image. C is the filter of radial cross section for various values of d naught. Selective filtering, band reject and band pass filters. Table shows the expression for ideal Butterworth and Gaussian band reject filters. W is the width of the band, D is the distance d of u of v from the center of the filter, d naught is the cutoff frequency, and n is the order. There are applications in which it is of interest to process certain band of frequencies or small regions of frequency rectangle, in which filters in the first category are called band reject and band pass filters or band pass filters, and the filters in the second category are called notch filters. Let us discuss band reject and band pass filters first. A band pass filter is obtained from a band reject filter given by h band pass of u comma v is equal to 1 minus hbr of u comma v. That is 1 minus h, that is band reject filter of u comma v. Example, you can see a band reject Gaussian filter in the figure. The figure A is a band reject Gaussian filter. Corresponding band pass filter, the thin black border. This is the B is the corresponding band pass filter. The thin black border in A was added for clarity. It is not a part of the data. Notch filters. Notch filters are most useful of the selective filters. Notch filters rejects or passes the frequencies about the predefined neighborhood of the center of the frequency rectangle. The general form is HNR of u comma v is equal to pi of k from 1 to q hk of u comma v into h minus k of u comma v. h minus k of u comma v. H suffix k of u comma v, h suffix minus k of u comma v are high pass filters whose centers are at uk comma vk and minus uk comma vk. Distance calculations for each filters are carried out using the expressions dk of u comma v is equal to u minus m by 2 minus u suffix k square whole square plus v minus n by 2 minus uk whole square to the power of 1 by 2. D suffix minus k of u comma v is equal to u minus m by 2 plus uk whole square plus e minus n by 2 plus vk to the whole square to the whole equation 1 by 2. Okay, this completes this notch filter. Now we will go for MCQs. Smoothing in frequency domain is achieved by attenuating which of the following component in the transform of a given image? A. Attenuating a range of high frequency components, attenuating a range of low frequency components, all of the mentioned, none of the mentioned. Answer is A. Attenuating a range of high frequency components. Since edges and sharp transition contribute significantly to high frequency contents in the gray level of an image, so smoothing is done by attenuating a range of high frequency components. Which of the following are considered as a type S of low pass filters? Which of the following is considered as a type of low pass filters? Ideal, Butterworth, Gaussian, all of the mentioned. The answer is D. All of the mentioned. Because the low pass filters are considered of three types: ideal, Butterworth, and Gaussian. Which of the low pass filters covers the range of very sharp filter function? Ideal low pass filters, Butterworth low pass filter, Gaussian low pass filter, all of them. The answer is A. Ideal low pass filters. Because ideal low pass filter covers the range of very sharp filter function of low pass filter. In a filter, all the frequencies inside a circle of radius d naught are not attenuated, while all frequencies outside the circle are completely attenuated. The d naught is the specified non-negative distance from the origin of the Fourier transform. Which of the following filter characterize the same? Ideal filter, Butterworth filter, Gaussian filter, all of the mentioned. Answer A. An ideal filter, all the frequencies at a circle of radius d naught are not attenuated, while all frequencies outside the circle are completely attenuated. The characteristics of the low pass filter h of x comma y are dash as a dominant component or origin as a concentric circular component but the center component, all of the mentioned, none of the mentioned. Answer is C, all of the mentioned. The low pass filter has two different characteristics. One is a dominant component or origin, and another one is a concentric circular component about the center component. Which of the following defines the expression for BLP? HU of order n, where d of uv is the distance from the point u of v, d naught is the distance defining cutoff frequency. 1 h of uv is equal to 1 by 1 plus du of v by d naught to the power of 2 pi 2n. B is h of uv is equal to 1 if d of uv is less than or equal to d naught, 0 if d of uv is greater than d naught, all of them mentioned, none of them mentioned. The answer is A. That is h of uv is equal to 1 over 1 plus d of uv by d naught to the power of 2n. The LPF is a Butterworth low pass filter and is defined as h of uv is equal to 1 over 1 plus d phi by d naught into 2n. State the statement true or false. BLPF has sharp discontinuity and ILPF doesn't, and so ILPF establishes a clear cutoff between passed and filtered frequencies. True or false? False. ILPF has a sharp discontinuity and BLPF doesn't. So BLPF establishes a clear cutoff between passed and filtered frequencies. A narrowband reject filter is commonly called as notch filter, bandstop filter, delay filter, all the mentioned. That is notch filter. A narrowband reject filter is also called as a notch filter because of its higher quality factor, Q greater than 10. Find out the application in which narrowband reject filter can be used. Embedded system, biomedical instrument, digital computer, none of the mentioned. The answer is B, biomedical instrument. Narrowband reject filters are used in biomedical instruments for eliminating undesired frequencies. Which filter attenuates any frequencies outside the pass band? Band pass, band reject, band stop, all of the mentioned. A band pass answer is A, band pass filter. A band pass filter has a pass band between two cutoff frequencies FH and FL. So any frequency out this pass band is attenuated. Today it will end this session. So thank you very much.